Hopefully by now, you've absorbed enough chemistry knowledge that with just a look around, you can spot chemical change occurring everywhere. Now think about change in organic molecules. Wine ages, mellowing and changing its flavors, maybe food spoiling, creating acrid and unpleasant compounds. Organic chemistry is special because it focuses so intensely on chemical reactions like those I just mentioned, and also on how we can use them in a directed fashion to create new and useful compounds, from solvents to building materials to drugs. The process of designing and carrying out an organic synthesis reaction can be very complex, and it's a topic worthy of a course all its own. Our task in this lecture is to get just a small sampling of the factors that go into understanding and using chemical changes in organic molecules. Such factors can affect very specific changes to molecules or groups of molecules, creating all new compounds that can serve a number of versatile roles in our world. During our discussions on rates and reaction mechanisms, we thought a little bit about how chemical reactions might proceed. We discussed the concepts of activation energy barriers and the formation and subsequent consumption of intermediates. But we stopped short of considering exactly how the bonds in those compounds broke and formed. It's really not enough to ask if an intermediate or a product is lower in energy overall. We have to ask if there's a reasonable way that bonds can break and form to accomplish the conversion. Now, there's no better branch of chemistry than organic chemistry to demonstrate this principle. Let's consider how bonds might actually break and form using a relatively simple reaction. Let's consider the reaction between hydroxide ion and methyl chloride. This reaction is expected to produce alcohol known as methanol and a chloride ion. Now, the questions we have to ask here are, where are the electrons going, and can they get where they really want to be in order for a reaction to take place? Now, you'll notice here that my hydroxide ion is going from an oxygen with 3 lone pairs and a negative charge to a OH or hydroxyl group bonded to a carbon. So we know that the electrons are coming from the hydroxide ion to form the new bond to the carbon. We also can look at the chloride and know that this bonding pair of electrons here must be making its way onto the chlorine atom to create a chloride ion with a full octet but carrying a negative charge. So if we want to show this reaction in motion, we have to highlight the important groups here. And then if we have a nice computer like we do here, we can animate the reaction and actually show the lone pair electrons of the hydroxide making their way in to take over that bonding location and kicking out the chloride. But we don't always have access to technology like this. Sometimes all we have are pen and paper or a chalkboard. So how do we convey the motion of the electrons that we just saw without actually animating them? And the answer is we use arrows. So here's an example of the exact same mechanism shown in a non-animated version, using just arrows to depict the flow of electrons. Here I have a curved arrow starting at my hydroxide lone pair, which points at the carbon where they'll be going to form the new bond, and an arrow starting at the middle of the bond that will be breaking, showing that those electrons are moving toward the chlorine. And of course, this leads to the products that we anticipated. So using these curved arrows to show the flow of electron pairs allows us to show a non-animated version of a chemical change taking place, one that a trained chemist can then reconstruct in their own mind and begin to understand how electrons and atoms are moving as these reactions are going on. So by considering 2 crucial questions, where do electrons want to go, and is there a pathway for them to get there, we can start to elucidate and even predict how conversions of organic molecules will take place. When designing an organic synthesis, researchers have to ask a lot of questions. Naturally, that first question is, what do I want to create? Usually, the structure of a product is predetermined. We know that we want to try a new drug with a methyl group here or a hydroxyl group there. So, of course, knowing where we want to go is essential. Now, this usually means carefully drawing out the structure of interest and considering what structural elements it has. But knowing our ultimate location isn't the only critical information. We have to consider where we should begin our synthesis as well. And we have to settle on our starting materials. The chain of logic most often used is called retrosynthetic analysis. In this technique, we start from the ultimate goal and ask ourselves, from what starting materials can I make this product? Next, we go to our lab inventory and we look for those materials. If we can't find them, we go back to the drawing board and ask, how can we make those starting materials from other compounds? The process is continued until, eureka, we find starting materials that are available or on hand, and we're ready to head into the lab and run the reaction in the forward direction. It's this process, the solving of the synthetic puzzle, that many organic chemists will point to as one of their favorite challenges. You can think of it just like any other puzzle, like Sudoku or a crossword. Once you learn the rules of the game, there is a practically inexhaustible supply of challenges to solve. So before we can go about solving such a puzzle, we have to learn a few of the rules. Now, to that end, let's investigate just a few reactions in the truly massive library of organic reactions at the disposal of the organic chemist. Nearly 200 years have passed since Friedrich Wöhler's famous urea synthesis tipped us off that organic chemistry doesn't really require organisms at all. And in that amount of time, we've learned a tremendous amount about how organic molecules and functional groups can be created, combined, broken down, and interchanged with one another. Over the past 2 centuries, scientists have uncovered hundreds, if not thousands, of types of reactions that can be used to create one organic compound from another. Now, we want to track how electrons flow when reactions take place, so we have to take a few moments to define a few of the players in these general forms of reactions. Nucleophiles are defined as a species with regions of dense negative charge and lone pair electrons that can be donated to a bond to relieve that charge. So, nucleophiles are looking for a positive charge. In other words, they're nucleus-loving, hence the term. Conversely, an electrophile is a species with a region of dense positive charge buildup and the ability to receive new electrons to form a bond that relieves that charge. So electrophiles are looking for a negative charge. They are electron-loving. So if nucleophiles are out looking for positive charge and electrophiles are out looking for a negative charge, then nucleophiles and electrophiles are out looking for each other. For example, hydroxide ion would be considered a good nucleophile because the OH- ion has not only a full unit of negative charge localized on it, but also plenty of lone pair electrons to use to attack an electrophile. Now, an electrophile might be something like methyl chloride. Methyl chloride contains a polar carbon-chlorine bond. Now, in some cases, we're going to see what are known as leaving groups. Leaving groups are atoms or groups of atoms that are capable of breaking loose from the electrophile and taking their bonding electrons along with them. So when these species are all considered, we can usually answer question 1. Where do the electrons want to go? So the next question to consider is, can they get there? Let's begin by considering substitution reactions. Recall that organic compounds are built on a stable carbon scaffold that acts as a sort of support for the functional groups that give them their reactivity and properties. When an organic chemist sets out to make a new compound, he or she is rarely forced to start from the absolute beginning. Often, there are available compounds that have the right carbon scaffold, but they have different functional groups or substituents than the new target product. One of the more common substitution reactions that organic chemists use to effect these kinds of changes is what's known as a nucleophilic substitution. I've got an example of a nucleophilic substitution mechanism shown here, one in which there's a fluoride ion, which is going to react with methyl iodide to displace the iodide ion and create a compound called methyl fluoride. So the reason that this reaction works is because the electrons from the fluoride ion would rather be involved in a bond than those in the iodine or the iodide ion that results. And you may ask yourself the question, why is that so? Isn't fluorine the most electronegative element of them all? And the answer to that question is yes, it is, but it's also very small. So the negative charge on my fluoride ion is occupied in a relatively small volume. So this is a very strong, dense negative charge. Whereas iodide ion, as we know, has a very large electron cloud and can distribute that charge over it. So under appropriate conditions, this transition can be coaxed into happening. Now when this happens, we call the fluoride ion a nucleophile. That's because the electrons on my fluoride ion want to react with a nucleus. They want to get rid of that negative charge by attacking a nucleus. We call the carbon or the substrate that will be attacked the electrophile, and that's because this carbon here is part of a polar bond in which the dipole is pointing towards the iodine. So that carbon is already electron deficient and would like to receive those electrons. And when these two get together, they displace iodide ion, which is the leaving group. And that is, of course, more stable than fluoride ion under the conditions that I'm going to use for this reaction. So this is a very simple substitution reaction, but this scheme can be seen used over and over again with rather complex scaffolds and electrophiles and nucleophiles and leaving groups to create a number of different chemical changes in the lab that we like to accomplish as synthetic organic chemists. So this simple substitution gives us a clear illustration of how electrons might relocate during a reaction to reach a new, lower energy state. Now, this is where the reactivity of functional groups comes in handy. Their unique reactivity means that they can be targeted and changed when exposed to the right reagents under the right conditions. If we want to place a stronger nucleophile on a location that has a good leaving group, we can simply use a substitution reaction. For example, methyl chloride can be transformed into the alcohol methanol using a hydroxide ion. Because the hydroxide ion is a good nucleophile and the chloride ion is a better leaving group, we can expect this substitution to take place. Now, a more complex example of substitution involving these two motifs is the interconversion of alcohol groups by turning them into chloride groups. Wait a minute, you might say, is that even possible? How can we accomplish the reverse, placing a less nucleophilic chloride and removing a more nucleophilic hydroxide? Well, the answer is we actually don't. We use a different reagent altogether. Alcohols like this methanol can be converted into alkyl halides like methyl chloride, but we have to use a different reagent called thionyl chloride. Now, the actual mechanism of this reaction is a bit more complex, with the alcohol first reacting to form a better leaving group before being attacked by a chloride nucleophile. It's a clever way to get rid of that hydroxyl group and get a chlorine atom in its place. But why would anyone really want to do that? Well, now imagine that you are Leslie Howe, a chemist working for Tate & Lyle in 1976, and you're trying to synthesize this, a molecule of sucralose. It's complex looking, isn't it? Now imagine trying to create this molecule using organic reactions of only the most basic carbon-containing molecules. Challenging, to say the least. But Howe knew better than to do that. He worked smarter, not harder. Sucrose, the naturally occurring sugar, is very easily extracted from plants like sugarcane and can be purchased in large quantities at low cost. Now, Howe devised a reaction scheme using thionyl chloride to effect substitution reactions at 3 of the hydroxyls in sucrose. In a relatively simple process, he was able to create sucralose, a non-caloric sweetener with remarkable similarity to sugar. Now, just by changing those 3 functional groups, Howe was able to create a molecule with a sweetness hundreds of times greater than sugar's. Although it tastes very sweet, the compound cannot be broken down or stored by the body the same way that sugar can. So, it doesn't serve as a source of energy. It also can't be broken down by most bacteria, a process that promotes food spoilage. Furthermore, sucralose is very stable over a range of pH and temperature conditions, and this allows it to be used in baking applications just like sugar. It's a wondrous product created by substituting just 3 atoms on the sugar molecule. I give Howe a bit too much credit here, though. In truth, he didn't know that sucralose was going to be the hit artificial sweetener that it had become. He was actually synthesizing various derivatives of sucrose, exploring their properties for several different industrial uses. He simply had the good fortune to have been misunderstood by his lab assistant, who was told to test the material, but instead tasted the material. Fortunately for his assistant, sucralose is non-toxic, and as he quickly discovered, very, very sweet tasting. Naturally, this happy accident altered the focus of Hal's research and led to one of the most profitable artificial sweetening products ever created. Another classic organic reaction mechanism is the elimination reaction. This somewhat scary-sounding name isn't really meant to be. It's simply used to imply that some sort of small byproduct is removed or eliminated from a larger starting material, not unlike a decomposition reaction. A very simple example of this is the formation of unsaturated hydrocarbons containing double or triple bonds. They form from saturated hydrocarbons which have only single bonds. Now, we call hydrocarbons with a double bond alkenes, and those with a triple bond alkynes. Now, let's focus right now on making alkenes. The simplest example of this is the production of ethylene gas from ethane gas. Now, in the case of this reaction, 1 mole of hydrogen gas is lost for every mole of alkane converted into an alkene. This process is called dehydrogenation, and it takes place at very high temperatures in the presence of special catalysts. This is one way that we get ethylene gas. Ethylene is a potent plant hormone used to signal fruits that it's time to ripen. It's also a very useful starting material in many organic synthesis reactions because it contains a pi bond. Remember that pi bonds involve electrons held not directly between two nuclei, but in the region defined by overlapping p orbitals, just above and below the internuclear axis. This makes pi bonds somewhat reactive, and their introduction into hydrocarbons can lead to materials which other reactions can be used to specifically modify them at the site of the double bond. But this simple method of dehydrogenation creates a mixture of unsaturated hydrocarbons that have to be isolated from one another, usually by distillation. All of the carbon atoms in an alkane have carbon-hydrogen bonds that can break to go on to form the product, so one carbon is really just about as good as any other. This problem can be surmounted, though, using elimination reactions that can be site-directed by using alkyl halides rather than alkanes as the starting materials. For example, consider dehydrogenation of hexane. This reaction can create any of 3 structural isomers of what we would call hexene. Hydrogens, they abound on this molecule, so dehydrogenation products will be messy and complex. They'll have to be separated by distillation at the cost of time, resources, and lower yields. But what if instead we heated 1-chlorohexane? In this case, the weaker carbon-chlorine bond means that the chlorine atom will be part of the elimination product. A strong enough base can remove a neighboring hydrogen as a proton, releasing the chloride ion, leaving group as a byproduct. And because of the location of the chlorine, the double bond must be on the terminal carbon of the molecule. Addition reactions can be thought of as the reverse process of the elimination reactions that we just discussed. When pi bonds on a compound are converted into sigma bonds, a great deal of free energy can be liberated because of the reduced enthalpy of the new bonds in the products created. Perhaps the best example of this is the Nobel Prize-winning process that was developed by French chemist Paul Sabatier in the early part of the 1900s. Sabatier didn't really invent the process of hydrogenation, but some would say that he set us on the path to perfecting it. Sabatier used metal catalysts to facilitate the addition reaction, creating a way to more efficiently perform this reaction. Now, it wasn't long before his technology was adopted and tuned by chemists trying to find ways to improve the food supply. You've probably heard of the term hydrogenated oil lately. Lately, hydrogenated oil has gotten a fair bit of bad press because we've come to realize the deleterious health effects that it can have. But in the early part of the 1900s, saturated fats were sought after foodstuffs, primarily because they tend to be solids and they can last much longer on the shelf. What I'm showing you here is a molecule of one of those oils that's in cottonseed oil that Sabatier wanted to hydrogenate. You'll notice that they have a series of double bonds here within each of these tails inside of that molecule. And the goal is to get hydrogen to add to those. But the problem is that hydrogen actually makes a pretty strong bond to itself, and it's rather fussy about getting on there. So instead of just putting the two together and hoping a reaction will take place, we use a platinum catalyst that weakens the bond between these two hydrogens and allows a reaction to take place in which the hydrogens add across the double bond, replacing the pi bond between these two carbons with new sigma bonds to the hydrogens. This is what we would call a partially hydrogenated oil because I've only added hydrogen to one of those double bonds, and this is where that term originates from. But organic chemists don't have to stop with simply adding hydrogen. Any number of other elements and groups can be added to molecules using the same strategy. Now, in certain situations, we need to add new substituents and functional groups to molecules at a specific location, and alkenes give us a way to do this. By starting with the proper alkene, synthetic organic chemists can be sure that addition of a number of diatomic molecules occurs across a double bond at a very specific location. Consider this problem. My synthesis goal is this molecule. This could be called a 2,3-dichlorobutane. Chlorine gas, just like hydrogen gas, can be added across a double bond using this strategy. But the location of the chlorine atoms in my product matter. What we would call 1,2-dichlorobutane is a completely different molecule with different physical and chemical properties. In short, location matters. If I'm working on synthesizing the next great dry cleaning solvent or refrigerant, I have to get those locations right. So, which starting material would you suggest we use for our addition reaction? Now, clearly, we need a 4-carbon chain with a double bond, right, a molecule that we would call butene. But that double bond could be in one of two distinct places. If it's on one of the terminal carbons, we would call this molecule 1-butene, or alpha-butylene. If instead the double bond is in the middle, we call it 2-butene, or beta-butylene. Now here we'd have to use beta-butylene because we know the addition will take place at the double bond itself, which is shared across the second and third carbons in the chain. Water is a remarkable compound. Abundant, non-toxic, remarkably stable. We often take its presence in the world around us for granted. It serves and sustains us in a number of ways, nourishing us as a beverage, acting as a solvent for everything from medicines to detergents, transferring heat in useful ways via steam, and many, many other uses. Now, water, it turns out, is no less useful to the synthetic organic chemist. From a free energy perspective, water is pretty stable. With a Gibbs free energy of formation of around -200 kilojoules per mole, chemists often exploit that stability by tying the formation of water to the formation of a more complex product that they want to make. This is an exploitation of Hess's law. Including a highly spontaneous process like the formation of water in a chemical reaction helps us to lower the overall free energy change of that process. So when water is formed as a byproduct of a reaction combining two organic compounds, we call the reaction a condensation reaction. Examples of condensation reactions include the formation of pleasant-smelling compounds like esters, which we make from acids and alcohols. Conversely, water can sometimes be an agent of destruction, splitting larger compounds into smaller ones by incorporating itself into those smaller products. This type of reaction is called hydrolysis, from the terms meaning to break with water. Condensation and hydrolysis reactions, building up and breaking down organic molecules respectively, are responsible for much of the change in the flavors of wine, as the acids and esters naturally in the wine build up and break down over time. This alters the bouquet and the taste of the product. They're all going on inside your body right now, too, building up and breaking down proteins that make up your muscles, as well as the glycogen and fats that are storing energy in your cells. Not to be outdone by the human body, chemists often use condensation and hydrolysis reactions to create useful products as well. And a few of the simplest and most time-tested products that we rely on use these types of reactions. One very simple and familiar example of how chemists can use reactions involving water to make useful products is in the synthesis of aspirin. Now, aspirin can be made from a starting material called salicylic acid. Salicylic acid itself is actually the compound that gives you pain relief when you use aspirin. The problem is that if you were to consume salicylic acid directly, it tends to cause a lot of irritation in the stomach. So, chemists have devised a way to create a simpler molecule, an easier molecule for you to digest. And that is, in one way, by reacting salicylic acid with acetic acid. Now, under the proper conditions, we can get this reaction to form the molecule aspirin and a molecule of water, which helps to energetically drive the reaction forward. So this is what we would call aspirin. And when you ingest this molecule, it's less irritating to your stomach. But once it reaches your bloodstream, it quickly hydrolyzes right back into salicylic acid, the molecule that actually gives you pain relief when you take aspirin. And so in this case, we have a reaction that shows beautifully how both the production of water in condensation reactions and the consumption of water in hydrolysis reactions can be used to create valuable materials that can be used, in this case, as medicines. We'll see water make more appearances in a few of our lectures as we discuss the chemistry going on around us in our world. For now, though, I think we've accomplished our goal of seeing how important the role of water can be in the creation of useful compounds, both as a byproduct in condensation and as a reagent in hydrolysis. As with so many of our topics, we've really just begun to scratch the surface of the discipline of synthetic organic chemistry in the past 3 lectures. Over the past 200 years, this well-developed chemical science has blossomed into a discipline all its own, one which many chemists spend their entire careers trying to better understand. The variety and versatility of organic compounds and the reactions in which they participate are phenomenal, and I hope that I've succeeded in piquing your curiosity about them. But our time with organic chemistry in this course is over. So let's sum up our final organic chemistry lecture before we move on. Let's review. Having just explored the structures and physical properties of organic compounds, we asked ourselves a question. How do we convert one organic compound into another? We started by thinking about how synthetic organic chemists might go about solving a synthetic problem, by thinking about the product he or she wants and working through a synthesis essentially backwards, stepwise, until identifying a starting material that's available or suitable. Then we tried classifying organic reactions in a very general way as substitution, elimination, or addition reactions. And then we took a brief look at an example of each kind. We saw how substitution reactions can be used to create new compounds from old by altering the identities of functional groups or substituents, as is the case in the popular sweetener, sucralose. We took a look at elimination reactions and how they can be used to create compounds with carbon-carbon pi bonds, which are usually somewhat reactive, and can be used as starting materials in other reactions, like our third class, addition reactions. Now, we thought about addition reactions, which are essentially the reverse process of eliminations, in which pi electrons from multiple bonds become sigma bonding electrons to new atoms, giving chemists a way to introduce new functional groups to molecules. And finally, we took a bit of time and considered the role of water in organic chemistry. We saw how it can be created as a byproduct in condensation reactions, which tend to build up larger products by connecting to smaller organic compounds. And this was the case in forming aspirin from salicylic acid and acetic acid. We saw how its consumption in hydrolysis can be used to break down larger organic molecules into smaller ones, like the conversion of aspirin back to salicylic acid and acetic acid once it's in your body. Next time, we're going to move on from traditional organic chemistry concepts, but we're not going to abandon it completely. Instead, we're going to consider what happens when some of the organic reactions we've already learned about are used not just to join 2 small molecules together, but hundreds, thousands, or even more. Synthetic polymers are the next step on our tour of the science of chemistry.